next speaker is Wayne Hayes, who will be talking about extracting structural information from images of spiral disk galaxies.
So although I don't think I can claim to have the resonance of Hal, I hope that I'm loud enough. I actually hate microphones. Can you hear me at the back all right?
Yes.
Okay, good. So I'm Wayne Hayes, and a lot of the work was done by my graduate student Darren Davis, and we also have an undergrad working with us called Randy Reyna, and he wrote some beautiful visualization code that I'll be talking about. And then we were talking about automatically extracting structural information from images of spiral galaxies. First of all, the Hubble classification scheme is pervasive, and everyone uses it, and it's been around for almost a century now. But I think it has a few disadvantages. For one thing, it's a discrete classification, and galaxy morphology is not discrete, it's continuous. It's also obviously somewhat subjective and quantitative, and I think the previous talk pointed out very beautifully how we need something that's objective and quantitative in order to make detailed comparisons with theory. So what we've created is an automatic method for extracting structure from images of galaxies. I'm not going to go into a lot of detail about how the method works. We started off with the data set of Sloan. The Sloan survey lists about 1 million objects as being galaxies, although it's difficult to, it doesn't specify whether it's a spiral galaxy, an elliptical galaxy, or anything else. So we went to the Galaxy Zoo folks and asked them, could you please send us a list of 30,000 Sloan objects, or send us the list of all things that the humans of the Galaxy Zoo project have classified as spiral galaxies. And Stephen Bamford, the head of the Galaxy Zoo project, very kindly provided us with a list of 30,000 galaxies that were classified as spirals according to the humans. This is just one example here. So our code accepts as input PNG images, JPEGs, or FITS images. And without going into a lot of detail, we cluster the pixels in the image based on something called orientation. And if you want details, you can read about the paper. I don't have time to describe it now. And that's based on an orientation idea from Kim and Au from his thesis in 2006. So let me talk about the picture. Here's an original image of a barred spiral galaxy. We do a contrast enhancement, and then using the orientation field provided by Au's method, we can cluster pixels into nearby pixels that have similar orientation, and that allows us to trace out clusters of pixels that represent spiral arms. So for example, this cyan cluster of pixels here represents a bunch of pixels that are all oriented similarly, which means the light in that area of the image is all kind of oriented in some certain direction. Once we have a bunch of pixels that have been clustered together, we can do a least squares fit of a logarithmic spiral arc to that cluster of pixels, and that allows us to then measure a pitch angle and a whole bunch of other parameters associated with that spiral arc. We can also find bars, as we see here. I want to emphasize that there's no Fourier analysis here at all. It's completely a computer vision algorithm that locally finds structures. There's no Fourier analysis. We also don't find forks, even though there's some places obviously where a human would say that's a fork in an arm. And our output is a list of arm segments and their parameters, including things like, like pitch angle. I want to show you some. So we've run this on 30,000 galaxies. I want to show you what some of the nicest ones look like. So here's a barred spiral. Pardon me?
Is it not cheating?
Why is it cheating? I'm going to show you some. I'm going to show you some bad ones as well. Don't worry. So I just want to show you that. When the structure is clear, the algorithm does very well. So basically, when a human would look at an image and say, okay, I can obviously find the bar and the arms there, our algorithm does a good job of finding them. So I'm just going to flip through a bunch of these fairly quickly. If you have any questions about any particular image, feel free to ask and stop. I can go back.
What are the colors?
So red arms, red arcs correspond to clockwise winding, and blue are counterclockwise.
And the
green is a bar. Yeah, green is a bar. That's right.
Oh,
so
that's good.
What's the giggling? You're not supposed to be giggling during these beautiful images.
Giggling with delight.
And here we are back at the beginning again. So those are some of the nice ones. And generally, like I said, when the image is obvious, our algorithm does well. So, validation. The Galaxy Zoo project is a citizen science project where human volunteers, about 250,000 of them, I imagine they're all 12-year-olds, can go to the web and be presented with a real image of a galaxy and some cartoon images, and their job is to click buttons on the web and decide which cartoons look most like the real galaxies. Now, I don't have time to go into a lot of detail about what this table is, but if we just ask the humans which direction do the arms wind and compare that to our results, then let me at least tell you what the rows and columns mean. So as we move to the right in this table, we are looking at increasing agreement among humans. So for example, this column here represents that the humans only agreed among each other 60% of the time in the winding direction. So this would be galaxies where it was difficult to discern the winding direction. In that case, our best algorithm, which is the lowest row here, agrees with the majority vote 95% of the time. So in some sense, we can do actually better than the humans in terms of deciding what the winding direction is. As we move to the right in the table here, when we get to the point where it's really obvious and 100% of the humans agree with each other, then we agree with them with the humans 98.4% of the time. So I think that's fairly good. We can also directly measure the winding tightness, or the pitch angle. So the pitch angle is the angle that this curve makes with a circle centered at the origin. So a tightly wound spiral corresponds to a low pitch angle, and a loosely wound spiral corresponds to a large pitch angle. So the humans were presented at Galaxy Zoo with these three images for each of the galaxies that they were presented, and asked, which of these cartoons most resembles the galaxy. We can directly measure the pitch angle of the galaxy. The diagram here shows the blue curve, for example, tells us what fraction of humans voted for tight when our measured pitch angle was small. So, of course, we get here about as good agreement as you can expect. When our measured pitch angle is small, a large fraction of the humans voted for tightly wound. And as our measured pitch angle increases, the fraction of humans voting for tight decreases, and the red curve is the fraction of humans voting for loosely wound, and the green curve is the one when humans voted for medium, and there's a little bump in the middle, as you'd expect. Okay. So again, given that the humans were not really given quantitative choices, I think we agree with the humans about as best as you can hope for. This is across 30,000 galaxies. Questions?
What are the dotted lines?
Sorry, this is the upper 25% quantile of human agreement, and this is the median. So the dark lines are when the humans were more sure.
Oh.
There have been about 100 galaxies. We've done 30,000 galaxies. Before us, there were about 100 galaxies that had pitch angles measured by hand. And this is just a scatter plot of our measured pitch angle versus a group in Arkansas that used a Fourier transform method. And you can see that at the very least, we always agree on winding direction, so this is clockwise versus counterclockwise. There is quite a bit of scatter, and I'll explain that a little bit later. It basically boils down to the fact that the pitch angle is difficult to define inside a single galaxy because different arms have different pitch angles. But in any case, there's obviously a good correlation, a decent correlation there. So, how are we doing for time? Our preliminary results. The first thing that we found is that it's really hard to define what the heck is an arm. What exactly is an arm? So I want to show you. Let's get out of the nice ones directory and go to the crappy ones directory. Actually not. I don't really call it that, but anyway. So here's an example of actually quite a nice spiral galaxy. It should be fairly, you can look at this and how do you have any problems with this? Here's the contrast enhanced image. I want you to focus on this region right here, where a human would probably say, this looks like a fork in an arm. Right? Here's an arm that's coming out here, and it forks into two pieces and goes on. That's certainly one interpretation of what's happening here, but I'm going to show you that there's actually several different interpretations. And these are all interpretations that our code has given at various points in its 3-year history, depending on small tweaks and parameters. The first thing to note is that actually there's an arm here that vanishes off the edge of the picture, and that's just because we didn't choose the right orientation there. There was an old version of the code that chose the right orientation, and there's actually an arm that goes all the way down here. So in this case, our code actually said that there's 3 different arms. There's the inner arm. Remember, our code does not actually look at forks. It doesn't actually find forks. It just finds arm segments. So according to this version of the code, there was one blue arm here, there was a green arm here, and a completely separate light blue arm there. And they all fit very, very well, logarithmic spiral arcs. That's one interpretation. Another interpretation is that, well, actually, that was never a fork in the first place. It's actually a continuation of this arm. And there is a little dark, let's go back to the contrast enhanced image. So there is a dark region here, but that's just your eye fooling you. Actually, there's a beautiful logarithmic spiral curve that goes all the way from here, all the way through there. And it's not really a fork from this arm, it's a continuation of that arm. So that's another possible interpretation. The most recent version of our code actually does this. It says that, well, actually, there's 4 different arms here. There's the inner one, there's a nice curve here, then there's a short arm there that's not really connected, and then this fork thing here, and we have the region that you might call a fork is a different arm with a really lousy fit. So the point is here is that it's difficult to define what an arm is, and so we actually stopped using the word arm. We meaning Darren and I stopped using the word arm a long time ago. We refer to arm segments instead. We just find arm segments. So now to get to something that might be astronomically interesting, one of the most interesting things we first found is that individual arm segments in one galaxy can have very different pitch angles. And so here's where our undergrad wrote this great visualization code. Here's one of our galaxies. So the rows here are individual spiral arcs. So this is, and they're sorted by length. So this is the longest spiral arc that was found. This is the second longest spiral arc. Third, fourth, fifth, etc. So, the thing to notice here is the pitch angle. The pitch angle of the longest arc is 13.64 degrees. The next longest arc has a pitch angle of 24 degrees. Now, you might argue with the interpretation of whether or not this is actually a good arc, because a good arm, because as I said before, finding arms is difficult. But this is not atypical. There are plenty of examples of galaxies, one of the next one for example, of galaxies where you have very well-defined spiral arcs that have very different pitch angles. Here's one where the top, actually this one actually has, they agree not too badly. This is the longest one is 17.3 degrees pitch angle, then 16. The third one is only 10, but it's kind of crappy. Here's one with an angle of 29 degrees. My point is that the pitch angle can vary quite a bit even within a single galaxy. And so defining the pitch angle of the galaxy is, as Rachel said, galaxies are not perfect. They're messy. Okay. Another thing that we might want to do is we might want to look at what a galaxy looks like across different wave bands. So let me now show you an example there. So this is some random galaxy in the G band. So this is a galaxy in the G band, same galaxy in the I band, and the same galaxy in the R band. Well, we have a minor technical difficulty here if we want to compare arms in different wave bands. So the G and the I have similar clusterings. So you can say, well, we compare this arm in one wave band to that arm, the same arm in a different wave band. The problem is, in the R wave band, that arm is not clustered the same way according to our algorithm. So now it becomes difficult to measure, to compare the pitch angle of this arm in one wave band to the same arm in a different wave band. So once again, we find that galaxies are not perfect, they're messy. So as I say here, it's difficult to match arm segments to each other in different wave bands for the purpose of comparing pitch angles across wave bands. However, for a sample of only 8, so we run our code on 30,000 galaxies, but this wave band comparison is actually quite difficult. We've only done it over 18 galaxies, and from a very preliminary standpoint, we have found that there's no obvious relation between the pitch angle and the wave band. And I'll note in passing that spiral density wave theory predicts that there should be a difference in pitch angle across wave bands, whereas, where's Leah? Leah I believe your theory predicts that there isn't a pitch. So from a very preliminary standpoint, we don't see a pitch angle difference across wave bands, but that needs to be looked at more carefully. We can also look at how average pitch angle changes with various parameters. I have observed a pitch angle increase with redshift, but I believe it's probably a selection effect simply because tightly wound spirals are difficult to see in fuzzy distant images. So I don't really believe that. However, there is, I think probably the most interesting thing we found is that there is a definite, although loose, correlation between pitch angle and color. So the color of a galaxy. Where are we? So this is for the nearest 600 galaxies from the spiral galaxies from the Sloan survey. With redshift less than, with z-value, redshift less than 0.02. And we can see that so the horizontal axis is color, red is towards that direction and blue is this direction, so it's color, it's U minus Z waveband. And the vertical axis is the pitch angle we measured. And across this 600 galaxies, the correlation coefficient here is minus 0.3, which is strong but not really tight. Here is, if we look at redshift between 0.02 and 0.04, again, there's about 3,000 galaxies here, and again we see a fairly strong correlation, although there's a lot of scatter of color versus pitch angle. I have no idea what could be causing this.
What do you mean by pitch angle for a galaxy?
So we take the length weighted average of all the arm segments. So the longest arm has the most weight.
Did you correct for inclination? Or?
Yeah. We make the image fit. We rotate it so it's face on. We align the image so the galaxy looks face on first.
How do you decide on the information?
We just perform a fit of a two-dimensional Gaussian to get the semi-major and semi-minor axis of the ellipse that best fits the entire disk of the galaxy, and then make it circular before we run our algorithm.
Does that work if you have strong spiral arms? Because
let's talk about it later. The short answer is I'm pretty sure it's yes. But anyway, so as we increase redshift, the correlation goes down. I think that might be a selection effect. I'm not sure. But in any case, I think this is the most convincing one here, right? For 3,000 galaxies with low redshift, that's what the correlation looks like, and it's color. I mean, why would color matter with orientation? As I said, there's no observable within galaxy pitch angle waveband correlation, and the caveat, as I said before, it's hard to measure, and it's a small 18 galaxy sample. I've already shown you all that. The last thing is we can, of course, we can look at the winding direction of all the galaxies all the spiral galaxies that we've measured, and ask: is there an asymmetry? Is there an abundance, for example, of clockwise versus counterclockwise galaxies? And both the Galaxy Project and Michael Longo and others have looked at this and suggested that the universe might have a hand in this, or at least locally it does. I'm running out of time, so just very, very briefly, our results mildly agree with Longo's results, but I'm not quite sure the p-values are all that strong. So that's it. Thank you.
We have time for one quick question.
So the correlation between color and pitch angle makes total sense to me, just because late-type galaxies tend to be bluer. There's a lot of scatter in that too, but they also tend to have larger, more open spiral arms, so I think that's completely expected. But so the question is, this handedness, I mean, that seems very surprising to me. How local is that?
Well, this is looking at all the spiral galaxies that we can actually determine handedness, which is about 30,000, between 30 and 50,000. I mean, this has been this is old. This is, people have been looking at this for, about 5 years. I'm just providing the first completely automated method.
I'm not saying I disbelieve what people said about it, I'm just saying I'm very surprised.
Of course, yeah. Cosmological theories assume the universe is not rotating. If that's not true, it throws a wrench into the works pretty seriously. So it's an important thing to test.
But it depends on where we are with respect to the galaxy, right?
It's probably an artifact of your eyes and detection, because Galaxy Zoo gave flipped images to
Right.
large numbers of people and got the same result. There was a
So it's not quite that.
same sense.
It's not quite that simple. But what I'm trying to hear is the first automated objective
But yours
measurement.
is new. Yours is new.
Yeah. But the p-values are, and a lot more data is needed and a lot more careful analysis is needed. How?
Well, I was just going to say, but your 30,000 galaxies were chosen by the Galaxy Zoo people.
Yes. There is a possible bias there. We are working right now on an algorithm to distinguish ellipticals from spirals using our own method here. Basically, if you try to find spiral arms in an elliptical galaxy, it doesn't, and that's a way to distinguish the two. But of course, that's a possible bias.
I think we're going to have to cut it out. So let's thank the speaker again.